Okay, so from now on we are going to talk about integration. So far we talked about the differentiation of multivariable function, and now it's time to think about how to integrate multivariable function. Okay. All right. So in a one single variable case, we have a notion of integration. When you learn that in the high school at the first time, I think you remember that as area. The integration is the area under the curve. So here is a summary that what you know. Probably you learned that the integration of a function whose graph is like this, and we have x-axis and y-axis here, and here is an interval a to b, and the area under the curve is the integration of fx from a to b, and that's the definite integral. So indefinite integral is a totally different notion. And if the graph is under the x-axis, we just put that negative sign to the area to define the definite integral. And also, right. So and also, you probably learned that as the limit of a Riemann sum. Not sure that that's the standard education in high school, but maybe. So when n goes to infinity, you take the sum over the interval of f of xi star xi xi let's say xi minus xi minus 1. So this Riemann sum represents sum of the rectangular area under the curve. It's approximate area under the curve. However, if I take the size of the interval to large enough, then this area of the rectangle approximates the actual area under the curve. So you probably learned that as also another definition of definite integral. So here's another picture. So here's rectangle. Sometimes it's above, sometimes it's below, like this. And it starts from x0 and ends at xn, and n is quite large here, and y is f of x, and the sum of n rectangular area approximates the definite integral, and when n gets large, then you get the smaller and thinner rectangular areas, and you sum those areas of the rectangles, then there is an error terms goes to 0, so we get the actual area under the curve. So when we have a second multivariable function, we can generalize this idea of definite integral naturally to the graph of the multivariable function. For example, if you take a two-variable function, you can generalize this concept naturally. So I'm not going to enlarge that slide. Just look at the bottom right corner of the screen here. So we have oh, sorry, what is it? So let's look at this one. So let's look at that double integral first. I will talk about the iterated integral later. So the double integral of a two-variable function, for example, f of xy, defined on the rectangular region D, x-axis runs from A to B and Y range from C to D. And we're going, that's how we defined is the following. So we're going to subdivide the interval A to B and C to D by n subintervals and m subintervals respectively. So in other words, let me draw that here. So we are having a rectangular region where the function is defined. So here is A, here's B, here's C, here's D. This is X and Y. And I'm going to subdivide x-axis. So here, subdivide axis. So this is x0 and this is xn. Okay. So I need to start from 0 index so that I get n subintervals. And again, I'm going to subdivide y-axis, or y range. Here, this is y0 and this is ym. Okay. And what we are going to do on each of these subinterval, for example, sub-region, for example, I take this part, I'm going to take a point inside of this sub-region, right? So let's say this region is xi comma xi minus 1 times yj minus 1. So I is either 1 to n and j is either 1 to m. Okay. I just take xi star yj star inside of this interval. In other words, I just take xi star lying in between xi minus 1 and xi, and yj star lying in between yj and yj minus 1. Okay? So you can simply take that point as a left bottom corner or top right corner or anywhere else on the boundary, or you can take a middle point here, doesn't matter. And then what we do is taking the function value at this point. So take f of xi star yj star, and then multiply that with the area of this subregion. So I'm going to write the width of this subregion as delta xi and height of this subregion as delta yj. Here delta xi is basically xi minus 1, and delta yj is yj minus 1. Okay, so for simplicity, I wrote this symbol. And think about what this represents. So we have area of the ij's subregion. Yeah, it goes a little bit far. Subregion. Okay. And then we multiply that with the value of function. So when I draw the graph of function over this region D, then I get a surface inside of this three-dimensional space, right? So suppose that I have another axis, z-axis, coming through the blackboard perpendicular way. Then I have a surface lying above this region D. So I take what I take as a function value is actually the height of the square, or the rectangular, the three-dimensional rectangular parts, and this gives the volume of that rectangular region, right? So this serves as a height under the graph of z equals to fxy at the point xi star yj star, right? So I'm going to take all of this for every subdivisions. So take sum, the big sum, where I range I from 1 to n and j to 1 to m. So rigorously, I have to put the two sigma sum symbols here. So, but you know what I mean. So ij both run from 1 to n and 1 to m respectively. Okay. So what we have obtained is the sum of volumes on each of subdivisions, subregions, with the height of rectangular same as the value of the function. If the value of function is negative, we are taking a negative areas. Okay, but let's assume that this function is a positive function. So I'm just taking a positive volume here. So this is the approximate area under the curve, right? So this is approximate, sorry, the area, volume under the graph, or did I say curve? Sorry, this is a approximate volume under the graph of f of xy. I want exact volume under the function, under the graph of function. What should I do? I have to increase the number of subdivisions for x-axis and y-axis. So I take the limit where n and m both goes to infinity, then this approaches to the exact, can you see this? Exact, yes, volume under the graph z equals to fxy. Okay, right. So this is the idea of double integral of two variable function. So in the slide, let me go back to the slide and read through what I wrote here. So we had subintervals and we have subregions, and so here we take the Riemann sum. It's called the Riemann sum. The name is not important. What important is why we are doing this. So we are taking the Riemann sum in order to get the sum of approximate the volume under the graph by the sum of volumes of rectangular regions. And if I take the number of subintervals to infinity, then this limit is called the double integral of this two variable function f over the rectangular region D. So the left hand side entire this symbol is the notation of meaning that it's a limit of this Riemann sum. So we have a two integral, and we have a D represent the domain, and we have an integrand f, and this dA is just the symbol. When you have an integral in the single variable case, you have dx or dy or something like that. But similar to that, we have a dA representing that this is the double integral, not the same as the single integral, single variable function integral. All right. So there's a big assumption when you define the double integral. So here is the if condition. If the limit exists when n and m goes to infinity, we denote double integral as this symbol, and we define that value as the limit. So Same thing for similar to the differentiability of two variable function. When you define a double integral, you have first guarantee that the integral exists. In other words, you have to check the integrability of the function. In other words, you have to check whether this limit exists. Okay. Normally, it's not an easy task to find out this limit exists because here, well, let me explain that later. Okay, so for now, just remember that we have to check. In principle, we have to check that this limit exists in order to talk about the double integral of two variable function. Okay, but many cases we're just going to ignore to check the integrability and then assume that this integral always exists, because it does, because we were going to talk about polynomials or exponential functions and etc., which are well-known functions such that the integral exists. Okay? So don't worry about checking the limit exists. But we are going to talk about more deeper meaning of this limit. But for now, let's talk about the integral iterated integral. So it's different from double integral. Sometimes, even after you learn this course, multivariable calculus, you probably confuse the difference between iterated integrals and double integral. So double integral is about the limit, okay? Iterated integral is just a way how to compute the two or several integrals on single variable functions. So for example, if you have a two variable function f of x, y, and we suppose that we wrote this iterated integral in this way. So here's a symbol. We take this antiderivative, integrand f, and we have dx and dy in sequel. So if I wrote this symbol, that means I take the integral of this function f in terms of x on the interval a to b, regarding that y is a constant. Okay? So it's similar to the partial derivative. When you take a partial derivative in terms of x, we take y as a constant, right? So iterated integral also do the same. So when you do this integral, we have only y left as a constant, as if it's a constant. But then, when you take an integral in terms of y, we take y as a variable, and then we do the integral again. So basically, we are doing two integral of single variable functions. Okay, it's very different notions. So iterated integral and double integral are different things. But one thing is clear, that the iterated integral and double integral both gives a number. Okay. So we're not talking about the indefinite integral here. So, like in a single variable case, in single variable case you have indefinite integral and definite integral are two different notions. But in the two variable or multivariable function case, we're not talking about indefinite integral. So everything has a value. Okay. So let's look at the theorem. So I'm not going to prove this theorem. If you take the course called analysis, I think it's a third grade course, you will learn why this is true. But let me just state the theorem. So if f is continuous on this rectangular region, then a double integral exists. Okay. So as long as you are talking about the continuous functions, then you don't have to worry about whether double integral exists, which means that whether the limit exists or not, it always exists. Okay. But let me tell you more about more than this theorem. So sometimes we're not going to talk about the continuous function. We sometimes talk about this continuous function at some point. But in that case, the double integral also exists. So as long as your points of discontinuity happens at small areas. So let's say, so theorem tells that f is continuous, then on the region D, then this exists. So you can always find the double integral. The remark is that if f is discontinuous at a point, let's say, let me write in the correct wording here. So if f is discontinuous on a subregion of D whose area is 0, then this integral also exists. What it means is that suppose that I have a function. Oh, maybe I need a very important notion here. Not just discontinuous, which area is 0, and f do not diverge on that region, then this integral exists. So for example, let's say I have x, y, z here. Let's say I take D as 0, 1, 0, 1. Okay. Let's say I take y goes to x region. Okay, so this is y goes to x. And suppose that I have function f whose value is 0 everywhere except on this yellow line we have value 1. Okay, here. So if I have function defined to be 0 or 1, let's say 1 first. If x equals to y and 0 otherwise, this double integral exists. And I know that this is 0. Why? So think about the process of finding the double integral. I have to take the subdivisions, okay, and then take the subregions and pick a point for each subregions and take that as a height. So when I take subdivision and further, what I get is smaller and smaller regions. These ones. So here. So maybe take these ones and here. So when I take the subdivision, the length of each subdivision doesn't have to be equal. Okay, I can take larger subdivisions or smaller subdivisions. It doesn't matter. Okay, so think about the subregions which contains a point on this yellow line. So there could be some zigzag way of these subregions, and I get smaller and smaller subdivisions. And for each subdivision which passing through this yellow line, I pick a random point. So I could pick a 0 point, a point where a function is 0, but also I can take a function value is equals to 1. But if I take a smaller and smaller regions, even if I take the point on the yellow line, which gives me a height 1, because the area of these subregions and some of these areas of subregions becomes 0, because when it covers this line, it could be covered by these small and smaller regions of these subregions. So the sum of the subregions, area of subregions, goes to 0. So by taking the smaller and smaller and smaller, smaller subregions, we can cover the line y equals to x only on this interval 0 to 1. I'm not talking about the entire line. I just take this line segment where x from 0 to 1 by sufficiently small areas. Okay. So basically, even though I take a non-zero height, the area under that point getting 0, so there's nothing to be added. So I know that this double integral becomes 0 because the other regions have height 0 everywhere. Okay. So when you think about the double integral, if function is continuous, you don't have to worry about whether this function exists. But if it has a discontinuous point, and you see that this discontinuity doesn't diverge when x goes, when I take point other than this y equals to x line, and I approach to a point on this discontinuous point, then always the limit is 0, so the limit doesn't diverge. So therefore, I can ignore what I have in this discontinuous region because this line has area 0. Okay. The similar way, if you have a one point of this continuous, and if the function doesn't diverge when you approach to that discontinuous point, then the double integral also exists. You can just ignore that point. All right. So let's think about the example here. So we have a function f(xy) equals to y over 1 plus xy. So I know that this is continuous from 0 to 1 cross 0 to 1. Find the double integral. So how do we take the double integral? You have to take the limit. It's not an easy task. So let me give idea how to approach this problem. So first of all, let's take, so our function is 1 plus xy, y, and let's take subintervals. Xi as I over n, okay, and also yj as j over n. So I'm going to take the same number of subinterval for x and y axis. Doesn't matter, n and m are independent, so I can make it equal. Okay. So double integral on this rectangular region is defined to be, when n goes to infinity, I take I and j both runs from 1 to n of function value f(xi) star and yj star times the size or width and height of these subregions, which is 1 over n, and 1 over n. Okay. I have to take this limit, but one thing is not clear. So we had xi star and yj star, which can be any number in between I over n to I minus 1 over n. So I have to pick a specific xi star and yj star in order to compute this limit. Otherwise, I cannot do this. So what kind of number I should take? So if I take, so let me ask this question: is it okay to pick, for example, the easiest way, xi star to be just xi, which is I over n. Let me write other place. So is it okay to pick xi star to be simply xi, which is I over n? Do you think it's okay? And why is it okay? So you could pick this number. That's fine. Why? So we had lied a little bit in the definition of double integral. So when we talk about the double integral, let me write that up again. So we had n and m goes to infinity, and I and j from 1 to n or m, and f of xi star and yj star, delta xi, delta yj. We say that if this limit exists, then the double integral exists. Okay? So it means that there are two things. I can take this subintervals, the lengths of subintervals, arbitrary size of subintervals. Okay. And how about this one? This is also arbitrary point in the subintervals. So it means that this limit must exist in order to in order to guarantee that the double integral exists, we need to guarantee that the limit exists for arbitrary point xi star and yj star on each of subintervals, and arbitrary size of subintervals on x-axis and y-axis. But here's an example. For example, if I take the x-axis, and here's our entire interval a to b. Suppose that I take x0 is fixed and xn is fixed. Suppose I take x1 at the middle, okay? And x2 to xn here. And then the way I take this subinterval is by fixing x1 to be always the middle of a and b, and make this other half to be smaller and smaller. What happens in this case? If I do this, then I'm not approximate this area under the or volume under the graph properly, because I can take any number in between these large intervals. What I'm expecting is my subintervals to be getting arbitrarily small for every subintervals. If I pick this kind of subinterval, then that's not what I'm expecting it. So the thing that I've lied in the definition is actually on this part. When n and m goes to infinity, this should be replaced in principle by the saying that the length of every subintervals goes to 0. So what I'm expecting to have this limit is by taking this subinterval, every subinterval getting smaller and smaller in size, so that this summation goes to a single, approaches to single value. Okay. But usually I take this subinterval to be equally sized subinterval. So when I take the n and m goes to infinity, that this part is satisfied. The length of every subinterval goes to 0. But in principle, in the very general definition of double integral, we have to replace this notation by the length of every subinterval goes to 0. In other words, maximum length of the subintervals goes to 0. But that's beyond our course. So anyway, let's go back to here. So we have equally sized subintervals, so it's okay just taking n goes to infinity, because in that way I have a smaller and smaller subintervals. So answer is yes. And answer is that's fine. This part is fine. And the question is, if I take xi start just as an 1 point xi as an example, and is it enough? The region is, we know that this is continuous, and we know by theorem the double integral exists. If it exists, then by definition, it means that whichever point I pick on this interval and each subintervals, the limit must exist to the same, limit must exist, and it must be all the same. Okay, so I can take any xi as long as it lies in the subintervals. So the answer is yes. And the region is the existence of double integral is guaranteed by the theorem. There's no here. So the existence of double integral is guaranteed. Okay. So let's try to compute. So here we have limit goes to infinity and ij from 1 to n of 1 plus I over n, j over n, and here j over n, and n square 1. So we have n goes to infinity of the limit ij from 1 to n of, let's say, and let's take n square multiplied on the denominator. We have n square plus ij and j over n here. So in other words, ij from 1 to n of n square plus ij over j. Okay, so it's not easy to compute this by hand, so you have to use the MATLAB. And also note that we have a double integral. We have to take the double sum. So we have to take the sum over I and then sum over j again. Okay. let's do that after the class. So that's how you do in general to take the double integral. Let's look at another example here. Let me enlarge this. Okay. So we have a function which is not a continuous function. So for example, this is a very weird function defined this way. So we have f of xy defined either 1 or 0. 1 if x or y is rational, 0 otherwise, which means that x and y are both irrational. Okay. Then it is not integrable on the 0, 1, 0, 1 domain. This one is x, sorry. This is x. It looks like y, but it's x. Okay. So this is not integrable, which means that we don't have a limit, which means that limit can be one thing, and there are two limits depending on the choice of subintervals and xi's and yj's. Okay, so let me explain that. That's a very typical example to show that not every function is integrable on the region. So I'm not going to draw. I can't draw because in 0, 1, 0, 1 region, how small I take each of the subregions here, there are always a point whose one of the coordinates is rational and both coordinates are irrational. For example, I take this region here. So here is xi minus 1, xi, and yj minus 1, yj. So this region, this subregion, contains both rational point or irrational point. It doesn't matter as long as one of the coordinates is rational, then it's defined as 1, right? Right. So just take a pick a rational point. Whichever real number I choose, that every interval contains a rational number, right? So I can take a rational number in this interval and a rational number in this interval. So let's say this is my xi star and yj star, for example, okay? And I can take a irrational point, so I get xi star star and yj star star. Okay. So when I try to compute the limit in order to get the double integral, xi star and yj star, if I use the xi star and yj star, which is rational, then this is always 1, right? And for each subinterval times yj, I equals to 1, ij equals to 1 to n and m, and take the limit, goes to infinity. So I don't have to worry about the value of this function because it's going to be always 1, because I'm going to choose always a rational point. So what I'm doing here basically is the sum of the areas of these rectangular regions. Okay. So what's the sum of the areas? It's 1, because basically it will cover the entire 0, 1, 0, 1 region. So it's always 1. However, if I take, instead of xi star star, then I know that this is always 0, there's nothing to be added. It's always 0. So we have two different values depending on the choice of value, choice of point in the subintervals. So the limit doesn't exist, therefore double integral doesn't exist. Okay. Okay. So, so here's what I just explained here. So we have 0, 1, 0, 1 rectangular region, square region, and for each subintervals, I can take a rational point or irrational point. Pick this as a denote each point as these symbols. If I pick rational point for every subintervals, I always get 1 for this part. So which means that I'm taking a sum of areas of subintervals, which becomes the entire area of this domain. It's always 1. And if I take irrational point, then value of function is always 0. So therefore, the limit is 0. So we have two different values of the limit, which means that the double integral doesn't exist. Okay. So once you understand the concept of double and iterated integral, everything is clear. I mean, everything is easy. So if you have any questions, just ask anytime. So here's an important theorem, the Fubini theorem, the first Fubini theorem. Okay. So it says that the double integral and the iterated integral are related. The condition is that the function must be continuous on the rectangular region. If it's so, then the double integral exists, and the value of that double integral can be computed by two different iterated integrals. The first one is taking an integral over y from c to d and then integrate over x from a to b. Or you can interchange the order. First take the integral over x and then take the integral over y. So be careful when you write iterated integral. You have to write the lower and upper limit of this integral, each integral, in the same order, and not same order, opposite order of this dx dy. Okay. So here's an example. So you have same example, but the previous case is finding the double integral by not knowing the Fubini theorem. Now we know the Fubini theorem, so we can integrate this by using the integrated integral. So let's do this. Okay, so let me erase this. So when I take 1 plus xy, y dA, so the interval of x and y are both equals to 0 to 1, so it doesn't matter here. So x plus y. First, let's try to take dx dy, which means I take integral over x first and then y. So consider y is a constant. So what do I get? So this becomes ln 1 plus xy from x from 0 to 1, right? Over dy. So 0, 1, and if I plug in 1 here, I get ln 1 plus y, and if I plug in 0, we have 0, so this is dy. Okay. So how do you take the integral of this one? Partial integral. So y ln 1 plus y. If I'm wrong, please correct me because I'm not good at calculation. So then minus 0, 1, 1 plus y, y, dy, right? So 1 becomes ln 2, 0 is 0, and minus, this can be written as 1 minus, it's a 1 minus, yeah, 1 minus 1, okay, dy, right? 1 plus y minus 1, right? So we have ln 2 minus y of 0, 1 plus ln 1 plus y 0, 1. So ln 2 minus 1 plus ln 2. So it's 2 ln 2 minus 1. Right? So what if I take y first? I think you could do that too, because so as long as you can do the integral for each steps, you can always change the order of integral. So you could done y over 1 plus xy dy first and then dx. So I don't have to worry about the changing the size, changing the symbols, because the intervals are the same. It gets a little bit complicated, but you can do that, right? So you have 0, 1 here. If I rewrite this as 1 minus 1 plus xy over 1 over 1 over x, and take dy and then dx. So take the integral. So you can take the integral of 1 over x because x is constant, because you can just take the integral of constant number. And also you can take the integral of 1 over 1 plus xy because just x is, consider x as constant. So you can do the rest of the calculation. So I think you will get the same answer. Let me show you what I wrote in the bottom right corner. Here. Right. You can do this calculation. All right. So what if we don't have a continuity in the theorem, which means that in the Pufovini theorem, okay? So so if you don't have a continuity condition on the theorem like way before here, we don't have a guaranteed definite double integral, okay? But in the Fubini theorem, if you don't have continuous, but however, in this theorem, you could have a discontinuous point as long as the limit doesn't diverge, then still the double integral could exist. But here, situation is getting worse. If you don't have a continuous function continuity, even though the limit exists, this equality doesn't hold. The double integral could exist, but sometimes this two integrated integral may not match. Okay, so for example, here you have a function, it's not really continuous at 0, 0, and I think it diverges, right? So the double integral could not exist either. But however, in the integrated integral doesn't exist either. So think about the domain 0, 0, 0, 1 cross 0, 1. So square domain here. And let's try to compute this dy first and then dx next. And try to compute this integrand. So the way how we get the antiderivative is just considering the x as a constant and using this integration technique in single variable case. So we have this as an antiderivative, y over x plus y squared. Just if you take the derivative of this fraction in terms of y, you get the exactly same integrand here. So plug in 1 and y, okay? And you get this result. When plug in 1, we get 1 over 1 plus x squared. When y is 0, it disappears. And then take the integral over x. So this is typical example of the derivative of arctangent here. So we have x from 0 to 1. So our value is pi over 4. So this is the result when you take an integral of y first and then x next. Think about iterated integral on the opposite order. So you first take the x and then next y. So when you take the integral over x first, consider y as a constant, and you get minus x over x squared plus y squared. You can check by taking a derivative of this fraction to get this one. And plug in x0 and 1, we get this one, and taking the integral again, we get minus arctangent of y from 0 to 1. We get minus pi over 4. So which means that this two iterated integral doesn't match. Okay, so the Fubini theorem doesn't hold. And also, this function diverges badly at 0, 0. If you draw this function again, it will diverge at 0, 0. Whenever it diverges, that means your height could be arbitrarily large. So your double integral may not also exist. So when you try to use the Fubini theorem, try to consider whether this function is function is continuous on the domain. Okay. So maybe we just finish this definition and then call it a day here. So we have a definition, another definition on the double integral. So here's the situation. So for example, if you have a non-rectangular domain, how do we define a double integral on this domain? So in previous example, for previous definition, our domain D is always rectangular from A to B cross C to D. What if I have a circular or wiggled domain? As long as it's bounded, I can take a large enough rectangular domain which contains the entire D and try to define a new function, large f, to be this way. So we have x, y inside of D, then the value of large f is equals to small f. If it's not in D, then the value is 0. So yes, this function is discontinuous on D. This function f could be discontinuous on D. However, the limit is always bounded on the discontinuous point. So here's the picture of what I'm explaining. So here's X and Y, and here's the region D. I take large rectangular region which contains D. Okay. And above D, maybe I had this graph of function. So this is Z equals X, Y. So only above D here. Okay. So I'm going to define another function whose domain is larger than D. So this function has value f at inside of D, and also, but outside of D it has value 0. Okay. So the red part is the graph of our new function large f. Okay. That makes sense. So we have a discontinuous at the boundary of D. It discontinuous. It breaks. The graph breaks. Okay. However, when I take a double integral, it's okay because the boundary of this bounded region has area 0. So as long as the discontinuous point, the set of discontinuous point has area 0, and the limit is bounded, then the double integral still exists. Think about the limit. So at the discontinuous point, like on the boundary point, the value of function goes to some bounded limit. So of course this is not continuous, so depending on the path it goes to different values. For example, if I approach to this boundary point on the outside of region D, then the limit is 0. But however, if I approach this point inside of D, it approaches along this graph of small f, so it also has a bounded number in not equals to 0, but anyway the limit is bounded. So as long as the limit is bounded and the set of discontinuous point has the area 0, then we have a double integral. So how we define the double integral on this domain is defining the double integral on this rectangular domain of our new function f. So we define on the right hand side double integral. Just take the subintervals smaller and smaller, and then take the area under volume over that subintervals, right? But that will be defined to be the double integral of this bounded region D. So basically, in the picture in the blackboard here, when I try to define the double integral over f, I'm going to take the subintervals which intersects D, okay, which only intersects D here, and take a rectangular region over that, the subregions which intersect C, and then take the height. I don't want to worry about the region doesn't intersect D, because the height will be always 0, because I take the value of function, and the value of function outside the region D is always 0. So when I take the smaller and smaller subregions, then there's the extra regions or missing regions and on these rectangular parts, but that goes to 0 and smaller. So the actual rectangular region approximates the area of D, and then the height is approximated more and more accurately by the function value small f. Okay. So that's how we define the domain, the definite integral on the bounded domain. And let me finish off by telling another theorem, second Fubini theorem. So There's a way, easier way to compute this double integral, not by introducing new function large f, but just using the defining equation of this bounded region. So for example, if you have a D defined to be two equations, two functions, g1 and g2. So here we have x range from a to b, and depending on the value of x, y range from g1x to g2x. Then this double integral, as long as this function is continuous on this domain, this double integral is equal to the iterated integral of y first and x next. So here y, the limit of y range from g1x and g2x, but that's okay because x is considered as constant, so we can just take these two limits as if it's just a number. However, if you take representation of d in an opposite way, so for example, if y range from c to d and x range according to y from h1y to h2y, then you can change the order of iterated integral to compute the definite integral. So here we have x first from range from h1y to h2y. So here's the picture. So as long as you understand the picture, everything is fine. So try to understand what I'm doing here in Fubini's second Fubini theorem. So here's range D. So here's A to B, and the bottom part is the graph of single variable function g1x, and on the top part of region D is the graph of g2x. Okay, this is x and y. So at each point x, the y can only range through g1 to g2. Okay. So I'm going to take an integration on y first. So by fixing x, considering x as a constant, try to compute the integration over this blue line here. Okay. So think about g1x to g2x of fxy of dy. So this is a function of x. What does it represent? What does it mean? So we have a graph of function fxy above this region D. Okay. So I had a section which slices the graph on this blue line, right? So think about. So here's another picture. Let me draw another picture here. D, and here is a graph of function. So I sliced it here. Okay. A little bit. Let me draw this again. So here's. Okay. So I sliced it, and there's a slice on this graph. What do I compute in this iterated integral? I compute the area of this slice of volume under the graph. So this is the area of the slice of the volume under the graph. G equals to fxy at x. So here's x, this is our x. Okay. Does it make sense? So let's say I'm taking this as, for example, large f of x. So and then next integral is integrating this large f of x. So integrating a to b large f of x. What do I get? So recall what we have learned in the single variable integration. So this is basically I'm taking f of x as area and d of x as the width of thin slice and take the sum of these volumes. So this is the volume under the graph. Z equals to f of y. Okay. So this is the width of thin slice, and this is the area of the slice, both at x. If you sum all this thin volume of thin slices, you got entire volume, right? So think about how we define the double integral on this region D. Basically, it's the area, I mean the volume under the graph, right? So that's the double integral over D of f of xy. Okay? So applying Fubini theorem is just a calculation. You can do this by MATLAB or other method. It's easy, but you have to understand why that happens, why this Fubini theorem works. Okay? So if you have any question, please ask anytime. So next time we're going to see some examples and talk about the triple integral. You can define an integration over 3 variable functions. Of course, once you do the 3 variable function case, you will imagine that this can be done on n variable function, but that's beyond our scope. So, and there's a last Fubini theorem on triple integral. And we are going to talk about the line integral. Probably we may not finish the surface integral this week, but I will try. Okay, so here's some problems. If you could solve some of the problems by yourself this week, try to do so. We don't have a homework this week. So that's all. So thank you for listening and see you on Friday. So Friday we will have offline class. So classroom is DGIST on the G floor on E7 building. And see you on Friday.